Hello students, welcome to my YouTube channel Dear Mathematics and also welcome to the chapter of set. This is the second video session of the chapter set. In the first video session, we have already discussed about the fundamental statements or fundamental words of the topic set. And also we had gone through the definition of set, and also we have seen the two types of representations are there to represent a set, and we have also gone for some of the examples that are based upon the representation of set. And in this particular session we are going to discuss about the types of sets, because there are several types of sets are there in the topic of mathematics. So let us discuss the several or different types of sets in the topic mathematics. So from the first type, and that is the empty set. So let us discuss about the empty set. So first of all, the question is, what is the empty set, or what is the definition of empty set? So first of all, let us discuss that empty set is otherwise called as void set, and also it is otherwise called as null set. So an empty set can be called as void set or null set. So definition of empty set says that if any set does not have any element in it, that means it has no element, then it is called as an empty set. So here it is, the definition is there. A set is said to be an empty set or a null set or a void set if it has no elements. It is denoted by the letter or by the symbol phi, and phi is a Greek word. Here it is psi, it is phi. In the roster form, phi is denoted by the empty curly brackets, having no elements in the two brackets. Let us take some examples so that empty set will be clear to you. It is the example number 1. Let a set is equal to x such that x belongs to n, that is x is a natural number, and x square minus 2 is equal to 0. That means you can see that first of all there are two equations, and as there a word and exists in between the two statements, that means we have to satisfy both of the conditions for the variable x. That means we have to satisfy the condition it must be a natural number, then we have to must satisfy that the condition x square minus 2 is equal to 0. If x square minus 2 is equal to 0, then x square is equal to 2, and then x is equal to square root of 2. But you can see that the square root of 2 is not a natural number. That means this condition out of the two condition is not satisfying here. So we cannot find out any elements of x here. That means A will be an empty set having no elements in it. So it is an empty set. So A is an empty set. Let us take another example. Example number 2. Let V is equal to x such that x is an prime number, x is a prime number greater than 2, greater than 2. So let us go through the prime numbers, because we have to also satisfy two conditions here. One is we have to find out the prime numbers, but then we have to find out the prime numbers greater than 2. And let us take here x is an even prime number. X is an even prime number. X is an even prime number and it must be greater than 2. The prime numbers are 2, 3, 5, 7, 11, 13. You can see that all of the prime numbers greater than 2 are of odd numbers. So we cannot find out a prime number greater than 2 and it must be even number, and we cannot find out any number in the list. So this set is again an empty set. Here V is an empty set, or also we can denote it as the symbol of phi. That means, so B is an empty set. Then let us move towards to the another example here. Example number 3. Let C is equal to x such that x belongs to n, 5 less than x less than 6. Again, we have to satisfy both of the conditions. That means x must be a natural number and then x must lie in between 5 and 6, and we have to find out that natural number in between 5 and 6. The natural numbers are 1, 2, 3, 4, 5, 6, but we have to find out a number greater than 5 and less than 6. But in between 5 and 6, we can find out, okay, it is clear, we can find out 5.5, 5.6, 5.3, but they are not the natural numbers. They are not the natural number, they are the decimal numbers. So we cannot find out any such natural numbers in between 5 and 6 such that x is a natural number and also it satisfies, it is greater than 5 and also less than 6. So this set is an empty set. We cannot find out any number like this. So C is an empty set, or you can say that void set, or also you can say that it is a null set. So it is all about the empty set, definition of empty set. That means the definition of empty set says that it is a set which having or which have no element in it. It is a special type of set. It is containing no elements in it, and it is denoted by 5. In the roster form, we have seen that what is the representation and how we can represent the null set or empty set in the roster form, and also we have seen some of the examples are there. Next, moving towards to the second type set, and that is singleton set. So the second type set is the singleton set, and it is the set which contains only one element in it. If a set contains only one element or the set consists of only one element, then that set is called as the singleton set. Let us go through some of the examples. Suppose I have taken a set here and it contains only the element 5. It is a singleton set. Okay. A is equal to set of the element 5 is a singleton set. Okay. Let us make it clear about the phi set. Here phi set is a null set or empty set or void set. Okay. It can also be represented by the form, this form. But suppose I have taken another set here. This is called as the singleton set. Because here this set is an empty set. It is not containing element. It does not have any element in it. But in this set, here we have an element and the element is itself phi. That means it is a singleton set. So you must be aware of these two conditions. So there is a big difference in between the phi set and the set of containing the element phi. It is a singleton set and this is an empty set. So it is, you can take it as another set and let us take it as V. Here V is a singleton set. Then let us move towards another example based upon the singleton set. Example number 2. Let V set x such that x belongs to n and x square is equal to 4. And we have to determine that it is a singleton set and we have to prove that it is a singleton set. If x square is equal to 4, that means we have to satisfy both of the conditions. It must be a natural number and then the square of that variable is equal to 4. And by consisting or combining these two conditions, we have to find out such numbers and we have to prove that that set is a singleton set. If x square is equal to 4, then x is equal to square root of 4. That means x is equal to plus minus 2. That means x is equal to plus 2, and also there exists another minus 2. But we have to consider only the natural numbers. That means we have to find out only the positive numbers. And here is the positive number, that is plus 2. That means it is the set containing the element 2, because we cannot contain this minus 2, because we are just satisfying the condition of x belongs to n. So you can see that the set V contains only one element, and that is 2 here. So it is a singleton set. So B is a singleton set. Then let us move towards to the pair set. So the set having 2 elements in it is called as a pair set. That means the set only having only 2 elements in it, then it is called as a pair set. That means if the set having no element, then it is called as empty set. If the set having one element in it, then it is called as singleton set. Similarly, if the set is containing only 2 elements, that means it is consists of 2 elements or 2 objects, then it is called as a pair set. Let us go through some of the examples here. Example, okay, here if I have taken a set A here and I have taken the elements 1 and 2, that means it is consisting of 2 elements only. That means is a pair set. Is a pair set. Then example number 2. Suppose I have taken let B is equal to x such that x belongs to n and x square minus 5x plus 6 is equal to 0. And we have to show that this set is the one of the example of the pair set. So first of all, we have to go through this condition and we have to find out the values or roots of x here. Then here it is x square minus 2x minus 3x plus 6 is equal to 0. That means it is x into x minus 2 minus 3 into x minus 2 is equal to 0. Then it is the multiplication of the x minus 2 and x minus 3 is equal to 0. That means x minus 2 is equal to 0 or x minus 3 is equal to 0. That means x is equal to 2 or x is equal to 3. And then we have to go through the second condition here. And the second condition is we have to verify that both of the roots must be natural numbers. And you can see that both of the roots are here of the natural numbers. So that means here the V set is the set of containing the 2 elements 2 and 3 only. And you can see that it satisfies the given definition here. So the set V is a pair set. And here you can write down B is a, so the set V, so the set V is a pair set. Okay, so it is all about the definition and examples based on pair set. And then moving towards to the finite set. So what is the definition of finite set and also what are the examples? And then moving towards to the finite set. A set is called a finite set if it is either a void set or the elements of that set can be counted. That means it has 2 definitions. If the set is a void set, then it is a finite set. If the elements of the given set can be counted or they are countable, then it is also called as finite set. That means let us take an example here. Suppose A is a phi set, or that means it is an empty set. Then it is finite. Because the number of elements are 0. The number of elements are 0 and we can count it as 0. As 0 is countable, that means we can define that no elements are there. That means 0 elements are there. That means it is counted. So phi set or empty set, it is finite set. And the second definition, if the elements are countable, that means let V set as it is containing 3 elements in it, 1, 2, 3, and we can count that. It is a finite set. It is a finite set because the total number of elements, and that is equal to 3, and it is countable. Okay. Then let us move towards to the very important, cardinal number of a finite set, because we cannot define the cardinal number of an infinite set. So cardinal number of a finite set, the total number of elements present in the given set is called as a cardinal number of the finite set. The number of elements present in a finite set is called the cardinal number of a finite set. If A is any set, then its cardinal number is denoted by number of elements present in that set, or also it is called as a cardinal of that set. Example, suppose I am taking, let V is equal to A, E, I, O, U. That means you can define or you can count the total number of elements present in that set V, and then the total number of elements is equal to 5. So you have to define, or we can define it as number of elements present in the set V, or also we can denote it as like this, and it is 5. So it is the all about the finite set and also the cardinal number of a finite set. Then moving towards to the infinite set. Then let us move towards to the fifth type of set, and that is infinite set. If the number of elements of a given set, that means the number of elements cannot be counted, then it is called as infinite set. If they are countable, then this set is called as finite set. If the number of elements are not countable, that not be counted, then it is called as infinite set. So let us take some of the examples, and you can see that all of the mathematical sets are called as infinite sets. From the natural number up to the real numbers, all of the sets are called as infinite set. That means the set of natural numbers 1, 2, 3 up to infinity, and it is an infinite set. Then the set of integers, it is 0 in between. Then towards the right hand side it is +1, +2, -1, -2. Towards the left hand side it is also an infinite set. Similarly, all of the mathematical sets you can take, and those are of the infinite sets. But let us make a difference here. Suppose I have taken a set A here, and here A is given that 1, 2, 3, 4 up to, but in the last part it has given a number, and that is 100. Then this is finite. Then this is finite. But if the set is given like that 1, 2, 3, 4 ... and the last number is not given to you, that means the last part is empty here, that means ... it is proceeding towards the right hand side, then it is called as infinite set. So these are the little bit things here, little things that you have to consider. What are the difference between finite and infinite in these two cases? Then let us move towards to the equivalent sets. The definition of equivalent sets tells that two finite sets, that means we have to consider only two finite sets. Two finite sets A and V are said to be equivalent sets if they are cardinal or same. That means if both of them are containing same number of elements, the total number of elements present in the first set must be equal to the total number of elements in the second set, and we can represent by symbolically, and it has number of elements in the set A must be equal to the number of elements in the set B. Let us take an example here. Let A is equal to is a set containing the elements 1, 2, 3, and V is a set containing the elements, suppose A, B, C. And here you can see that number of elements in the set A, it is 3, and number of elements in the set B is equal to 3. Then you can see that number of elements present in the set A is equal to the number of elements present in the set B is equal to 3. So the two sets A and V are called as equivalent sets, So it is all about the definition and the symbolical form, and then one of the example upon the equivalent sets, then moving towards to the equal sets, and then we will discuss what are the differences exist in between the equivalent set and also equal set. The definition of equal set tells that two sets A and B are said to be two equal sets if all of the members of the set A are also the members of V, and again all of the members that are present or all of the elements that are present in the set V are also the members of A. That means all of the elements in the A set and in the V set are very much equal with each other. So let us take an example here so that it will be clear. If the two sets A and B are equal, then mathematically or symbolically we can represent it as A is equal to B. Okay, let us take an example. Let A set is equal to 1, 2, 4, 5 and V set is equal to 5, 4, 1, 2. You can see that all of the elements present in the first set, A set, are also the elements or the members of the second set. And in the reverse order, we can tell that all of the elements present in the second set are also the members of the first set. So we can here write it as A is equal to B set. And again, by considering the previous definition of equivalent set, the total number of elements present in the A set is equal to 4, and also the total number of elements in the B set is equal to 4. That means they are also equivalent sets. So the two sets A and V are equal. That is, A is equal to B. Again, the number of elements present in the first set 4, number of elements present in the second set, it is again 4. So the two sets A and V are equivalent sets. That means every equal sets are equivalent sets. Each and all equal sets are equivalent sets. But let us see another example. If any equivalent set is a equal set or not. Is it possible that a equivalent set is a equal set or not? Let us take another example. Let A is equal to 1, 2, 3, 5 and V set is equal to A, B, C, D. And here the number of elements of the first set is equal to the number of elements in the second set. That means number of elements of A is equal to 4 and the number of elements in the set V it is 4. So the two sets A and B are equivalent with each other, or they are called as equivalent sets. But it is not possible to write down the two sets are equal because all of the elements of the first set are not of the members of the second set. Similarly, in the reverse condition, all of the members of the second set are not the member of the first set. That means A is not equal to B. But A is not equal to B. That is A and B are not equal sets. That means we can also again define that in symbolical form A is not equal to B. So every equal sets are equivalent sets, but every equivalent sets are not equal sets. Okay, let us write down the conclusion here. So the final conclusion in between the equivalent set and the equal sets, every equal sets are equivalent sets. What? Every equivalent sets are not equal sets. It may be, it may not be. It may be or it may not be. So this is the final conclusion in between the equivalent set and equal sets. Then let us solve some of the important problems based upon these types of sets. So here I have taken 5 examples are there, and we have to determine that which type of sets are there. So the first set is given at x such that x belongs to n, it is the set of natural numbers. But the second condition is x minus 1, the multiplication of x minus 1, x minus 2 is equal to 0. That means the numbers are x minus 1 is equal to 0 and x minus 2 is equal to 0. That means x is equal to 1 and x is equal to 2. And both of them are natural numbers. That means it is satisfying both of the conditions. So the set A, it is 1, 2 because both of them are natural numbers and satisfying the second condition here. So it is a finite set, and also it is called as a pair set. So it is a, you can write down here, it is a finite set, or also you can mention it as a pair set, because pair set is one type of a finite set. Then moving towards to the second question. And the second question is x such that x belongs to n, it is a natural number, and x square is equal to 4. Whenever x square is equal to 4, that means x is equal to square root of 4, that means x is equal to plus minus 2. That means x is equal to plus 2 and also x is equal to minus 2. But here x belongs to n, that means it is a natural number. So x is equal to minus 2, we cannot take this value, or we cannot put this consideration. So it is our variant consideration. So you have to take the only value x is equal to plus 2 because it is a natural number. So the required set V is the set of the elements only 2. So you can mention it as, or you can represent it as a finite set, or also you can represent it as a singleton set, because definition of singleton set says that it is a set having only one element in it. So it is a finite set, or also you can mention it as singleton set, because singleton set is also one type of a finite set, singleton set. So these are the two solutions of the first part and second part. Then moving towards to the third question. Okay, the third one is here, and it has been asked to find out which type of set it is. X belongs to n, that means it must be a natural number. But the second condition is 2x minus 1 is equal to 0, that means 2x is equal to 1 and here x is equal to 1 by 2. But x is equal to 1 by 2 is not a natural number. So we cannot put, or we cannot take or consider this element in our set, because it is not satisfying both of the conditions given in the set. So the C set is, phi, that means it is an empty set. It is an empty set. So it is of the empty set type. Then moving towards to the fourth type. And the fourth question is here, and it has been given that x belongs to again natural number, but x is a prime. It must be prime and also natural number. So we can find out in infinite numbers of elements are there, 2, 3, 5, 7, 11, 13, ... Infinite numbers are there, and they must be prime and they must be natural number. So it is a infinite set. So the D set, D is an infinite set. Then moving towards to the E set. Similarly, we have to define, it has been asked to x such that x is a natural number and also it is odd. So we can define 1, 3, 5, 7, 9, such like infinite numbers are there. We can define both of the way, natural numbers and also there are odd numbers. So again the set E is an infinite set. So these are the solution of these 5 examples. Then let us move towards to another example. Then let us come to the last example of this video session, and it has been given that find the pair of equal sets if in a given regions. That means we have to find out the equal sets here present out of the 5 sets. And the first example is that the first set is here, A is a set containing the element 0. That means a single element is present in the first set. So that is, it is a singleton set, and the answer is, it has been given already. Then the second set is, V is a set X such that X is greater than 15 but less than 5. That means if it is the number line, we have to find out such type of elements less than 5 and greater than 15. That means it is impossible to find out such type of elements are there. So that means it is a phi set. It is a phi set, or you can mention it as empty set. Then the third set is like X such that X minus 5 is equal to 0. That means here the set is 5. It is a singleton set, but it is very much different from this set and also this set. That means till now we have not found any set those are equal. Then let us move towards to the fourth set. It has been given that D is a such type of set X such that X square is equal to 25. If X square is equal to 25, then X is equal to square root of 25. That means it is X is equal to plus minus 5. That means both. There are two answers. One is plus 5, another is minus 5. That means it is a pair set. So the D set is a pair set containing two elements. One is plus 5 and another is minus 5. Then let us come to the final set. The fifth set is here, X such that X is an integral positive root of the equation X square minus 2X plus 15 is equal to 0. That means, first of all, we have to solve the quadratic equation. Here it is given that X square minus 2X plus 15 is equal to 0. Then it is X square minus 5X. Okay, it is minus 15. Then minus 5x plus 3x minus 15 is equal to 0. Then it will be x, taking x common from the first two elements, it is x minus 5. Then taking common 3 here, it is x minus 5 is equal to 0. That means the two factors are here, x minus 5 and x plus 3. And solving these factors, we can have if x minus 5 is equal to 0, then the answer will be x is equal to plus 5. If we are considering x plus 3 is equal to 0, then we are getting x is equal to minus 3. But according to the rule of the set, it has been asked to find out x is an integral. Integral may be of both sides. If it is positive or it can be negative. But then the term comes here positive. That means just only we have to consider the positive terms. That means x is equal to minus 3 is not receivable. That means we cannot pick out this term or we cannot pick out this root here. So just we have to consider the positive term because the term is here integral positive root. So the final answer or the final set of the given set E, it is in the tabular form, it can be mentioned it as plus 5. So out of the 5 sets, you can see that the C set is very much equal to the E set. That means here the two sets C and E are equal with each other. Or in the symbolical form, we can represent it as symbolically C is equal to E. So these are some of the basic examples based upon the fundamentals of sets. So in the next topic we are going to discuss about more on the chapter of a set. Till then, thank you.